Hello.
Hello.
Hi. Nice meeting you.
I think I'm the only one here.
I guess guests arrive sooner than the host.
I don't know. I'm waiting for him, as you do. How are you?
Good, good. Thank you. My name is
Dear
Tahsin.
Tahsin,
Nice
how
Nice
meeting
to
are
you.
meet
you?
Hi, Fatih.
Great to see you.
you. Thank you, Professor. You are late.
Yes, so Aydın Bey is an industrial, he's an electronics engineer actually, and he gave us a talk a couple of hours ago. He's refurbishing ultrasonic transducers. So he told us about ultrasonic transducers and their use in industry. Uh, and in this refurbishment, we may help him with the model analysis of these devices. So um, now, one of my students, you met him, I think, Ufuk, is going to give a presentation about those discs, piezo discs, and their model analysis. Um, so this is kind of a university industry or university academia partnership session. We are going to see whether you will be able to help Aydın Bey. So I missed you, by the way, a long time. We didn't see each other. All the fault is Mete because Mete didn't. Mete was very busy finding a job for himself. That's
Yeah.
one of the reasons I think why he couldn't send us the drafts of the papers. Uh,
Yes.
uh,
And I don't want to blame him only. It was me also busy with a few stuff, which was I gave more priority, to be honest. But
so
um, but yeah, I could blame him as well because I did not get his update. But that was the excuse.
yeah, yeah, he is not commenting still. We are waiting for his comments. We have more students actually. Maybe they will turn on their cameras. I think we are eight. We have 8 students. Not students because Mete is not a student anymore. Mete is actually a professor. He found a position for himself in a new university in
Oh,
Istanbul. Uh,
good.
so yeah, he's in a biomedical engineering department. Mete, why don't
Oh,
you
excellent.
talk about this yourself?
Yeah, I will let me just turn on my mic. Okay, I think you can hear me now.
Yes.
Uh, yeah, I found a position in Atlas University, which is based on which is founded by people who found a hospital. So it is very biomedical and medical oriented university. So I will be working there. Actually, for 2 months, I have some permission to not go to work at the moment. But 2 months later, at the beginning of October, I will be starting my job. I have finally found a job, dear Tahsin. So I am really sorry for not being around. You are very right to be pissed at me.
No.
But I am working actually right now. I am running our codes.
That's excellent news, and we could have done also more. It is not you only, you know that. It's just we planned it such that you are to blame. No, don't worry about it. We will fix that and we will get that done. Um, Mete, can you hear us still?
I can hear you very,
Yeah.
very less. Actually, we have some speaker problem here.
Okay. For acoustic guy,
Yeah.
Good job.
Just a moment. I'm just going to bring a cable here in order to
Yeah.
connect the computer with the speaker. So just give me a minute, please. I'm coming back.
Mhm.
Well, I want to talk to you, but I am not able to hear you. So sorry.
No problem. Can you hear me now?
How about you? Everything's all right? But you, I won't be
Ye-
hearing you. That's silly.
Yes, Mehdi. Yes, thank you. As you know, we got into biomedical as well. And my friend actually, remember Sebastian? The- I guess you cannot hear me.
Yok, duyamadık. Öyle mi? Ben mi açayım? Okay, I think now I can hear you.
Okay. So as you know, we were looking into some biomedical applications as well. If you remember with
Yeah.
the work with Sebastian about imaging and focusing and all of that stuff.
Mhm,
Yeah,
mhm.
so we are expanding on that. And also we got involved in kind of a couple of projects with USDA, which is the agricultural stuff, ARS, basically to design sensors, acoustic sensors, both for pollinators like bees and also for plants, to hear plants. So
Plants.
yes,
It's interesting.
plants make sound when they are stressed. You can tell
Yeah,
they're
actually, I
lacking.
have just recently read a book on that.
Yes.
Yeah. I recently read a book about that. Let me check its writer. Yeah, he claims that plants making noise and they communicate with each other and they help each other to heal. Yeah, ağaçların gizli hayatı.
So this is very unexplored territory. People are making it sometimes bigger than it is, sometimes smaller. But regardless, there are sounds emitted in the ultrasound frequency, and
Yeah.
you can detect them. And based on their frequency, you can tell the plant is stressed. And that
Yeah,
has
I am
been
just going to
investigated.
write the writer of the book here. The book that I'm reading right now.
Look at this one.
Vohleben.
The secret life of plants.
Yeah.
Yeah.
That's the same book that I was talking about.
So this book was written by şu şeyi kapatır mısın?
Kapatıyorum.
Peter Tompkins and Christopher Ward, who were, I think, both CIA. They openly say that. And
Hey, what does they
it's
have
a
to
very
do with
interesting
plants?
book, actually.
Hocam pozitif filme dönelim ya.
I read it, and it's fascinating. The plants makes noise and they communicate with one another, and so
Well,
is that the kind of thing you are working with
yeah,
right
this
now?
summer I got involved in that.
Yes, dear.
What we found out, and this is based on the papers I read, that plants make sound when stressed. Let's say if they
Yeah,
tested tomato and tobacco plants, and there were ultrasound frequencies emitted at a specific number of times when they are stressed. So you
yeah.
can tell based on the number, the frequency of the sounds emitted, the plant is stressed. But that is not yet related to deficiencies in nitrogen and other things. And interestingly, the roots make sound also.
Oh,
And yeah, and and also they hear sounds. Apparently, the vibration sound coming from the water. If you play the sound of water, the root plant will go that way. And another fascinating thing is if you have a bee, a pollinator, plants can sense the vibration and increase the sugar content in the nectar. Think about it.
We
So
increase the sugar content.
yeah, so there's a lot of ways you can manipulate that, and you can sense that. So we are working on that right now. This summer, it was a very busy summer designing
Mm.
materials for these applications.
Mm. That's
So
great.
yeah, I did not take a day off. So sorry, Mete,
Mm.
for being late. But I will get back to our papers. I promise.
Yeah. So I think we can get uh, going with our presentation. So they want me to close my speakers of the computer. Kapattım. Okay. Şimdi duyuluyor mu?
Benden çok ses geliyor.
O zaman kapat onu.
Sizin komple kapatma da. Benim bilgisayarla
Okay. Let me test the microphone here. Can you guys hear us? Duyuluyor mu sesimiz?
Evet, ben duyuyorum. Duyuyorum.
Zaten Ufuk konuşacak.
bundan konuşsun o zaman. Hoparlör olmadı. Bunlar yeterince ses geliyor zaten.
It's quite hot here, by the way.
To
Sen
tell me,
konuşursan
you don't want to be
yeterince-
in Texas right now.
Oh, yeah, you don't want to be in Texas right now. How hot is it?
We are prisoners at home. It goes to,
Wow.
I don't know, 40 degrees, 38, 40 degrees Celsius. And it has
Wow.
humidity too. Yeah, secret life of
Wow.
plants.
So let me introduce Ufuk Baler. Ufuk just defended his MSc thesis a week ago, actually. So his MSc thesis title was the piezoelectric surface acoustic wave actuators for
Excellent. I'm very
mass
interested in
sensing.
that.
Yeah, for mass sensing in liquids. Arkadaşlar bir oturabilir misiniz ya? Dikkatim dağılıyor. Hiçbir şey konuşamıyorum. And he did his master's together with Emek Abalı, who is our research associate, who is working in Uppsala University in Sweden. And we've been working for about 2.5 years in a national Turkish national science funded project, which is related with the fabrication of integrated sensor, integrated
Excellent.
sensor devices. And today he's going to present us some preliminary work that he did for the sensor design. The reason is because in the preliminary work that he did, he actually analyzed these discs, actually, piezoelectric discs, and it is related with what Aydın Bey has to, what Aydın Bey is actually asking from us. So thank you for being here, and I'm giving the floor to Ufuk for his presentation. Evet. Pardon.
Ya fazla video varsa sen kapatabilirsin. Aslında ben de izleyebilirsin.
Sizlerden ses gelmiyor ama ben sesi açınca duyuyorum ama.
Ufuk'un sesini açacağız. Ondan dinleyeceğiz. Galiba çünkü onun mikrofonu. Yani mikrofon sesini de aç ki duyalım insanların konuşacağını.
Okay. Sorry for the technical issue. I think we managed to start. Yeah. So this presentation is about thickness shear in piezoelectric materials, and I will give finite element solutions for the regarding problem. So I would like to first thank you. I would like to give my thanks to Dr. Oker and Dr. Abalı for their supervision and contributions for this preliminary work. So let me show you the agenda for today's presentation. I will give some introduction for thickness shear mode and its applications. Then the mathematical modeling of these kind of piezoelectric materials will be discussed. Then I will give some validation between FEniCS and COMSOL to show you that we can do this kind of simulations. And for a reduction of the current geometry, we utilize RVs. So I will give the RV application. Then for discussion, I will open the floor for questions, etc. So let's begin with thickness shear mode. As you can see here, so the piezoelectric material is located between two electrode layers, which are colored in a dark color, and these electrode layers or patches are connected to potentials from the terminals, and when you apply a potential to an electrode, there is an electric field between those electrodes, and piezoelectric effect shows vibration if the potential is a sinusoidal function, for example. And the resulting mode of vibration in this case is the thickness shear mode, which is shown, and as you can see, the the vibration or displacement of the particles in the bulk are in horizontal direction, which is shown by the cross-sectional view of the piezoelectric material. And there is no motion in the height direction in this example. So this application is actually used by sensing chemical agents in liquid environments. One side of the electrode is interfaced, or it makes an interface on the liquid environment, and they functionalize this surface, this electrode surface, by means of chemical manufacturing techniques. And when there is suitable chemical molecules, they are captured by the functionalized surface. And due to this capturing mechanism, there is an accumulation of mass, and this mass accumulation actually shifts the resonance frequency of the piezoelectric material. And so how can we model this kind of material? So we resort to mathematical modeling. So since we are using open source finite element program called FEniCS, it requires to have a weak form of the piezoelectric material. In this case, this is the weak form, which constitutes the mechanical displacement in the first line, and second line constitutes the electrical part of the problem. So we sum them up basically for the weak problem. But also we need to consider the constitutive behavior of the material, and the stress is the result of the deformation, which is linear strain. We use linear strain and infinitesimal strain. And as I mentioned previously, there is an electrical field, so the electric field vector is also present here. And as a result of these two, the stress occurs in the material, and electrical displacement also present because of the electric field and deformation. So, of course, as you know, the piezo materials are crystals, and they have some they have a crystal orientation in some planes, and when in practice actually they cut a geometry from the piezoelectric medium. So, for example, if you are using quartz, you can cut a rectangular prism from the medium, which is found naturally, and at some specific angles, it shows a specific vibrational mode. But this angle can be found in literature, or in literature basically. For to compensate this issue in the computational model, we need to convert the material unrotated matrices via the rotation transformation matrices, so that we get the transformed material parameters. And here's an example for the AT cut quartz. So AT cut requires 0 rotation about Z, minus 35.25 degrees rotation about X, and again we need to rotate it 0, so we don't rotate it 0 about Z axis, and the resulting transformation matrix is written like this. And here U is the displacement which is being solved in FEniCS. Electric potential is phi. Test functions for displacement and electric potential. Ni is the surface normal. Sigma ij is the stress.
Sure.
B is the electrical displacement. E is the electric field vector. Epsilon is the infinitesimal tensor. Elasticity tensor, coupling coefficient matrix, permittivity matrix, and density. So, for the model analysis of such devices can be conducted via by considering the response of these devices. So here, displacement is separated into two parts. One of them is temporal, and one of them is spatial, and one of them is temporal. So this assumption or physics is also valid for the potential. So basically, in time, there is a periodic response for each of these variables. And due to this constitutional behavior of these materials, there is an instant change between mechanical displacements and electric potential. So when you change one of them, the other variable is also changed. Basically, we can write displacement. I'm sorry, the inertial term or the acceleration in terms of the displacement. So because of this, we can create some mass and stiffness matrices. On the right hand side, you can see the assembled expression of the mass matrix. So as you can see, this approach, the simplification of the acceleration approach, is integrated into the mass matrix. Then, due to the coupling effect of piezoelectric materials, there are actually 4 stiffness matrices, and each stiffness matrix compensates different variables. For example, KUU is contributed by only the mechanical displacement variables, and KU phi is contributed by both variables u and phi. Actually, k phi u is the transpose of the previous one, and k phi is the contribution coming from only coming from potentials. So we create this generalized eigenvalue problem, and this matrix notation is actually an augmented notation. So we place those assembled matrices as shown, but there's a problem in this generalized eigenvalue problem expression, because the sum of the diagonal entries of the augmented mass matrix are 0. So because of this issue, we need to apply static condensation, which is actually written by which is actually derived from this basic algebraic operation. So we rewrite the problem in terms of u as the variable, and then so we come up with k star, which is condensed stiffness matrix, and this thanks to this condensation, the generalized eigenvalue problem can only be solved for u, which is the displacement, and it is the eigenvector. And the eigenvalues of the problem is the omega squared, which is the angular frequency, square of the angular frequency. And to actually validate our codes, we resort to COMSOL. So we actually solve the problem in FEniCS, but we also compare it with COMSOL simulations. And for a disk geometry, this is the mode that we are looking for the operational state of this kind of quartz disks. And we found that this eigenvector is obtained at 5.955 megahertz. And on the right hand side, you can see the COMSOL result that shows a very similar eigen mode, and this is found at 5.112 megahertz. So there is actually a difference between those numbers, and we think that this can be due to the mesh resolution or any difference in material parameters. But at least we observed that there is a correspondence between those results. And okay, we had the result. How about applying and modeling this kind of geometry via RV approach or representative volume element? So you can see if actually you can see some shaded rectangular prisms, and in the middle you can see a selected representative volume element, which is exactly the same geometry like the shaded ones, and we can apply periodic boundary conditions on the opposing faces of the geometry in direction x1 and x3, and top and bottom are let free basically. And when we solve the eigenvalue problem, we get the fundamental frequency for this geometry. This is only for demonstration purposes, so we are not after for the same eigenmode as in the previous one. This is just for the verification of the codes. So that geometry gives the fundamental frequency at 830 kilohertz. So there is a similar profile for the eigenmode, but in the transverse direction at 950 kilohertz. So we have another eigenmode, and it is a multiple of it is twice as much as the first one. So we get, for example, a different eigenvector which shows a deformation in thickness direction, and it basically a bulk wave, but the ends of the plate actually goes up and down in height direction. So there's a transverse direction deformation here, and you can see it goes on like this, and we get another bulk acoustic wave eigenmode. Then we just show you the some of the results of this eigenvalue problem. And for the discussion, I would like to resort some issues that we are dealing with right now, or we just want to implement in the future. So we sent a paper, and they give a feedback about why you don't apply FLOCA for this problem. So they are not satisfied with the approach, which is using the periodic boundary condition only. So we take a look at, and so FLOCA boundary condition is about solving a displacement, for example, from this equation. So U is the displacement, and A is a periodic function in the spatial in spatial form. So this periodic function repeats itself in the length of R1 in the computational domain. So it is the same value. But in order to implement this condition, we need to utilize I'm sorry, wave vector concept, which is an abstract concept. So the problem requires this is a similar expression that we are dealt with previously. So the eigen values are omega squared, and so U actually is also also depends on wave vector. So actually, this is not a complete theoretical presentation at this slide, because we just think about this solution, and we thought that, so is Floquet required for the present problem, TSH problem? And I think it's not required, because wave actually travels in only height direction, so there is no any wave propagation for example in plane. So I think we don't need to implement Floquet in TSH problem. In the TSH problem. So thanks for listening and taking your time. Yeah.
So thank you, Ufuk. Um, so you closed your presentation with a question, and let me just rephrase Ufuk's question one more time. We actually carried out a representative volume element method in order to find out the thickness shear modes in a plate. And we sent, and there were two responses. One of them was positive, but the other response was inquiring or asking us why we didn't implement Floquet boundary conditions in the periodic boundaries. So we didn't actually respond to this response. We didn't actually give an answer to this response. But instead, we decided just to implement Floquet boundary conditions. So, however, now Ufuk is asking the question whether that was necessary or not. He's basically saying that the waves were propagating in the vertical direction, not in the in-plane direction. So maybe that question was not relevant at all, and we could open the floor to discussion as the first point. If you would like to add your comments, we would be happy to hear about those first. And as the second point, we actually did carry out an analysis of the circular disk, which is more relevant with the ultrasonic transducers that Aydın Bey discussed in the morning. So we were able to carry out that analysis, and we could actually show you we could actually after the question answer period, if anybody is interested, we could show you how we run that. So if there are any comments, we will be, or questions, please go ahead. And
Yeah, so I have, before getting to the slide number 9.
Okay.
And you saw some differences between The
delay in the
if you check condition around this.
in this result actually there is no boundary conditions because thereafter for solving the eigenmodes this geometry in free space basically. So there is no boundary conditions applied for this geometry.
Are you using the same for both models? Because to me, and what you're plotting, I think let's wait for the screen to come back. Yeah, what you're plotting is, I believe, maybe the magnitude. Right? So this is the magnitude.
Sorry.
Yeah.
Sorry,
No
Tahsin.
problem.
Just,
I think one,
just a moment,
I may not be correct in
just,
comparing them
turning
because
off.
you plotted them also in
Right.
different scales.
Sorry.
So they're
You
not the
said-
same scale.
What is the scale issue that you were mentioning?
Yeah, so the range of the color range is not the same. One is going to 2.5, one is 2.
Uh-huh.
Yeah, so
So visually it's hard to compare as how what is going on, but based on the color codes here, what I see is mostly dominant in the boundary of the object, the difference.
The difference, right?
It
Um,
seems that the constraints were different.
um, well, we actually followed the console's tutorial in order to validate what we did with the other option we had was to use the console in order to look at the same problem. So we followed the tutorial actually in console first, and then we tried to apply the same problem. There is no restrictions on either one of the electrical or the mechanical displacement in none of
Yeah.
the boundaries in this case. There was no restrictions of such. The difference in the eigenmode frequency was probably because we were not using the material properties correctly at that time. Then we went through some more corrections, and in the actual solve problem or the surface acoustics wave problem that we solved in the framework of the project, we actually corrected and validated. But then Ufuk didn't go back, I think, and correct the material properties in this particular problem.
Okay, so this is not the issue. Okay,
So
so
the difference in the mode may not be an issue actually.
okay. So if you now the second question, the wave, if you're looking at the wave, depending on what you are looking at, right? So if you're looking at the wave, acoustic waves, you're right, but that acoustic wave in an elastic medium, which is your piezoelectric material, creates shear waves. So yeah, the acoustic wave in homogeneous, like when the air or in a homogeneous medium, you say, okay, well, acoustic wave is longitudinal wave. But when it hits and gets into the sensor, it does generate shear waves or P waves, right?
Right.
So it would be hard to argue that the acoustic wave is the longitudinal wave, and we should not worry about the shear waves generated in the sensor.
Okay. The shear waves, the thickness shear waves, are actually uh, traveling there. If you think about their direction of propagation, I think we are saying here that the shear wave, the thickness shear waves, are traveling in the thickness direction. Is that correct to say?
Well, thickness direction. Now that they also the
I mean,
Yeah, but as they travel in the true thickness direction because they're shear waves, they are stresses induced in the radial direction.
in, in this case, we are actually modeling an infinite plate. This is not the disk, but
Oh,
an
this is
infinite
not a
plate.
disk.
Yeah, this one is the picture that he showed with the like the honeycomb with the RV, red RV in the middle. This is
Right.
like a infinite plate. So we are trying to find out the thickness shear in an infinite plate.
So what you're saying is you're saying I'm not concerned about the propagation in the radial direction.
In the transverse planar
Yeah,
direction.
yeah. But
So we
I
are we are
think
not concerned about that because we are actually solving for the bulk and shear wave propagation in the thickness directions. So is Floquet boundary conditions would they be relevant? That's our basically question because that would be the basis of answering this rejection basically by the reviewer.
I think we need to think about this, but I believe one can argue, and that can be a very small significance. Or one can argue that you are ignoring in a limited dimension around the boundary, along the element that you are finding, the stress is applied on the element sidewise or radial direction. So that may reduce the fidelity of the answer, but whether or not this has any practical limitation and if it is significant or not, it probably is not.
Hmm.
Um,
Hmm.
I don't know. What do you think?
Now, I think changing the size of the RVE may be an answer to this question. If you change the the dimensions of the red colored RVE and, for example, make a slightly wider cross section, would you still be able to get the same values for these eigenvalues? If they don't change, it means that the transverse dimensions are not relevant with the wave propagation in the out of plane or vertical direction. Would you agree on that?
Oh, so you're saying if you increase the size of this center element highlighted,
The
oh,
cross section only, not the
yeah,
depth
the
or
cross section, then what?
then these values are not going to change, I believe. And
What is not going to change? Sorry, I did not get it.
the the eigenvalues,
Okay.
the eigenfrequencies, if they don't change, it means does it mean that the wave propagation results in the vertical direction are uh, independent of the RV dimensions, the cross-sectional
So,
RV dimensions?
so the way you are considering the model, um, it has the relation of the displacement in the weak form initially presented. So the displacement is coupled with the electricity generated, right? The
Yeah,
potential.
right.
And none of those displacement, they are integrated over um, over the element, right? So there is a special integration in those weak forms, right?
Hmm.
So how come changing the domain, the size of the domain has no effect on that eigenvalue? I mean that equation. If you go back to the weak form, you are performing integration over domain.
Mm-hmm.
So you're saying this domain can be of any shape. Go back to the weak form, please, Ufuk.
Can you go
Yeah,
back? Yeah.
this integration is done on the volume, you see?
Yep.
So you are saying if I change that volume, nothing will happen.
Um, well, we are using periodic boundary conditions to model um, the way this element, this volume behaves. So um, what we are I am not basically saying that it will the complete results, all the results are going to be the same, because there are further on towards the higher frequencies there are going to be other mode shapes. There are going to be mode shapes that are associated with surface waves that occur on the upper surface and the lower surface. They will probably change, but what I'm saying is uh, the frequencies at which the thickness shear modes occur, they may not be affected. And if we find out that this actually is so, we didn't test this, by the way. This is just a hypothesis
Yes.
that I
Yes.
just made up. If it's true,
Then
it
it
turns
doesn't matter. And I agree with you on that. And I agree with that. That's why I said it may not have any practical importance, you know. But
Mhm.
what I'm trying to say, I'm trying to understand the reviewer point of view in terms of the accuracy of the analysis. So if
Uh,
you want to make a argument with that reviewer, you need to clarify in a good understanding that what this is what we understand also matches in these senses, which has no significance. And then you say, okay, in the paper, you clarify that these significance, since they are not important in the direction of the wave considered in the performance of the limit,
right.
and we are being ignored in the study, you know? So you clarify that in the paper and you make an argument as why this is not important, and that can be accompanied with a few numerical experiments by changing volume, as you mentioned. And
Mhm.
then that should be enough for the reviewer to be convinced. Or, you know, if you want to make a argument with the reviewer, I'm trying to think of what should be provided
Mhm.
as a supporting material.
Mhm. Mhm. Mhm. Yeah, but um, well, this was actually about a year ago, and we didn't argue about this, and we didn't have this idea about. I mean, we just accepted his view, and we said that, oh, he's right, so we should apply Floquet boundary conditions, and we missed that. But now we come back and think about it. We said that maybe what we did was sufficient, and in this case, for these modes that occur at lower frequencies, we are not actually interested in what Floquet is going to uh, give us. Maybe I'm not sure. So anyway, uh, thanks for the comments. I
Yeah,
think
absolutely. Sorry, I'm thinking on the spot. It's not, I did not think deep about it. I'm just
yeah, yeah, just
sharing my thoughts, thinking out loud.
mhm, yeah. So the second problem was the disk problem. This was an infinite plate. The first problem was a disk problem, and the second problem was an infinite plate, basically. So Idenbay is interested in these disks because they are used in the ultrasonic transducers. They are also called Langevin transducers, I think, as we have seen this in the literature. So, well, Idenbay, this is what we have to do in order to model. So, did you find it relevant, or do you have any comments about this?
Our piezo disc are ring, not
Yeah,
plates.
yeah,
First.
yeah.
And second, we use D33
Right,
form.
right. Yeah, yeah. These have not been. These were results that we obtained in order to just validate our model with COMSOL. And now, of course, if when you brought us the new geometry and you are interested in the thickness pressure mode, probably we could call it, because it's like a in the
Yes.
thickness mode, as you said. So we will have to look into different part of the we would have to look into the different part of the frequency axis in order to find or locate what is relevant for your application. Basically, it is going to be at a lower frequency, probably at a much lower frequency.
Yes,
We
much
didn't
lower.
look at- Mhm.
Much lower frequency because of the dimension of the piezo ceramics. If piezo ceramics dimensions bigger, then frequency is lower.
Yeah. Um, actually,
Also,
we could. Mhm.
excuse me, also different kind of material. We use PZT type of piezo ceramics.
Okay,
This
sure.
is you said crystal, I think.
Quartz crystal. Right?
Quartz crystal, yes, correct.
So we can change the material type, the geometry, and then we can search for the relevant mode, and then we can. I think we can find it.
Sure.
Maybe in the near future, in next week, we can meet and maybe go over the solution procedure. We can show you the solution procedure, and then you will have a better idea about how we go ahead with the solution.
Okay.
Um, so
But excuse me, I told you as I told you in the morning, model analysis results kind of dependent of the mesh size. I consider this with ANSYS because somewhere in the presentation, Ufuk said maybe there will be a mesh size problem. I'm not sure, but I don't want to comment. But my experience says mesh size or number of mesh doesn't change the results very significant.
okay, yeah. Any other comments?
From previous eigenvalue analysis, I can relate to that comment. You see, it does affect the calculation, but the first one, even the coordinates kind of in range, it's not like significant. When you increase the number of meshes, you basically you converge basically, but very little changes.
Yeah.
Yeah.
So that should not be something
Yeah.
significant if you have enough degrees of
So that 20% difference would not be explained by mesh convergence, right?
Yeah, I agree that it is not likely.
Yeah, it is probably not from the mesh, but probably there was a lot of confusion about the way the quartz material properties were modeled in the literature. Even in IEEE reports, there were differences in different years. Like in 1949, there was some report about in a standard about the quartz properties, and then in 1978, and in 1987 there were two more reported results, and so there was some discrepancy about some left-handedness and some right-handedness, and people tended to be confused, or they seemed to be confused about them. So we were, of course, as newcomers to this problem, we didn't know what to use at that time with quartz, and we had to also figure out about the coordinate transformation operations, and we also had a mistake there, and we corrected that mistake after we solved this problem. Now I believe if we go back to this problem and carefully put our material properties, then this will resolve this discrepancy probably.
And also, I need to mention that in COMSOL, for example, it will tell you what equations they're showing using or the material properties. So you can at least run for the same, because that's another numerical method. And if you look at the manual, it will tell you what equation they're solving, what are the assumptions, and what are the material properties for that you are considering in the code, in the program, so that you can match it and make sure. Also, I would say, Ufuk, you need to use the same visualization profile. If you are using JET or whatever, use the same and within the same scale, because what you are giving us is not really, I don't know if they are matching or not. I have to imagine if we use the same color scheme and the same scale, what it would look like.
Okay, thank you. Thank
Yeah,
you.
cool.
May I say something?
Sure.
Another issue, I'm not a theoretical one. I'm not an academician, but I saw your visual results. In my opinion, I expect symmetrical visual shape, like COMSOL. I don't know. Please don't misunderstand me. But left side of the visual is not symmetrical.
Okay. Your visual.
This is just what I expect to see. I just want to say.
All right. I actually, Aydın Bey, when we look at this, it's not coming up. Hangi internete bağlısın ya? MW'ye bağlı. There's a problem with our internet connection. The figures you are meaning you are referring to the circular disc shapes, right? In COMSOL and in the FEniCS, right? The two circular discs that we compared. That's what you are referring to.
Yes.
Right.
Yes.
So if you look into the COMSOL tutorial, it is not perfectly symmetrical either. As a matter of fact, in the center of the disk, there's supposed to be an area with low displacements, and you don't even see that in the COMSOL. There is a kind of so it's not that is not even perfectly symmetrical. You would have to look into it with more detail. You can actually take a look at the link that I posted in our website, and you will have a chance to look at the COMSOL result. You will see that that is not even either symmetrical. It is nearly symmetrical. It is not perfectly symmetrical. As you can see, so the blue. So this area here, can you see this area here? This area is supposed to be bluish, but there is a kind of a disruption here. It becomes light blue. However, in our model, you see that it's like a pancake with a blue mid layer, and our model seems to be a little better even.
Yes, correct. Yes,
Yeah.
that is correct.
I'm not sure why this is not perfect symmetrical. It's probably because of the discretization. It's like the physical, the fact that you have actually discretized an actual perfectly circular cylinder causes this slight, slight, um, let's say, deviations from the symmetrical behavior that we expect to see.
Okay, this is just an idea. I don't want to be rude. I'm not a
Not at all.
theoretical
No,
one.
no, no. I understand your point, but so so uh, I would just like to open the floor for further suggestions. Would anybody like to discuss any topic of maybe future collaboration or any suggested ideas? Uh, yes.
Excuse me, did you? I never used console before. Did you make any harmonic kind of analysis with this project or thesis?
Actually, in our in Ufuk's presentation, he used FEniCS, and we only use console in order to validate the FEniCS results. But
Okay.
you are right because console can do harmonic analysis, and we were not able to do harmonic analysis in FEniCS because that the version that of FEniCS we were using didn't include complex number support. So uh, uh, one of the reasons why we are going to have a workshop tomorrow for the installation of the new FEniCS, and we would like to move our code from the old FEniCS to the new FEniCS in order to be able to do the harmonic response analysis first, and then also in order to be able to implement these Floquet block boundary conditions that are going to be necessary for like a dispersion analysis of uh, of piezoelectric structures and metamaterials also.
Okay.
Uh,
I think thank you, Folk. You did a good job.
Yeah.
What I would like to say is the next step would be, I don't know, this is what comes to my mind. The next step would be to look into the surface acoustic sensors. If you can capture, it's not only the disk, what I mean with all the forks and the wave traveling in the substrate, and kind of measuring how that is affected by the phenomena you are sensing. So that takes you to the next level of developing sensors based on surface acoustics, and that has many applications. If you can link that to the optimization of the size of the substrate and also the basically the forks, receiver and sender, and how they will affect, can be tuned to better sense a phenomena you are sensing. They can be anything from a gas, let's say CO2 presence, to anything, to sound, to touch screen surfaces, right? Has very wide range of applications, this technology. So I think the next would be like more, not only not staying with the disk, kind of validate and finish this. I'm not suggesting to jump, but also extend it probably to those applications, because that has commercial interest as well, industrial interest as well.
uh, Actually, what Ufuk presented was not his entire thesis, but only a portion of it. So, in the end of his presentation, in his master thesis, um, it, there were also transient type of analysis of the structures that we analyzed by model analysis. So we did the transient analysis, and as a result of using very small time steps, we were able to do some FFTs on those signals, and that revealed, for example, that the response that we obtained from exciting the structure by an IDT as opposed to the mode shape, the electrical mode shape that that is found in the model analysis. If you approximate that by putting some pair of electrodes on the surface, and if you approximate a sinusoidal wave with some electrodes, the result is like you also have some mixed modes. You have some other frequencies or some other resonances that also appear around that the major mode that you are trying to excite. So that was the main outcome, I think, that he.
Are you measuring also or simulating the electric output?
Yes.
From the, right? Are you doing that? The
The
equations you are solving for them.
Now, if you are looking, I mean, if you are interested in measuring the electrical output, then it's like you have another extra port.
That's what I was suggesting, to have the extra port, you know, to
Right.
basically.
Right, you have an input port, and then there's an extra
receiver.
Port.
Yes.
Right.
So
right.
that when you sense whatever in between.
Right, you have the sensitive layer in between them, and it actually turns out there are two types of SAW sensors. One of them is like this delay line concept, and there's another concept called the resonator, on which you can actually cover the sensitive layer on top of the input port, and there's a single port actually. There are only a single port. And is that right? Is it or the two ports are very close to one another, rather, something like that.
In the resonator, yeah, I still remember they are very close. Two ports are very close.
And in one of them you have the reflectors, in the other one there are no reflectors. So there are two designs on the SAW devices. We are actually on the resonator. We preferred more of the resonator. Because the electrical team, there's an electrical engineering part which measures the produced circuits. So they actually have designed an electrical circuit to measure the resonance frequency, and the shift in the resonance tells us whether there is enough mass has landed on this selected surface or not.
Excuse me, you can use a signal generator and a oscilloscope to measure the resonance frequency. You don't need any different kind of device like impedance analyzer. I have a impedance analyzer, but your project is out of its range.
Yes, you are right. Actually, they have devised a special circuitry where they attach the sensor that was produced. So we actually have a means to produce the sensors in TÜBİTAK, and then those sensors are sent to ITU, and the team in ITU actually they produced some circuit, where you can actually insert the produced sensor, and they can actually measure. There's, I think, they have a circuit which kind of it actually it scans a range of frequencies to find the resonance. It's kind of a scanner.
Yes. And it's called network. Yes.
Analyzer. Network analyzer.
Network analyzer. Yes, correct. Excuse me. Your project is up to 5 gigahertz, right?
No, it's like 40
45
megahertz.
Yeah,
So
so
40 megahertz or something like that. That's where it works.
40, okay. Because there are many different parameters if you want to measure the system with this kind of high frequencies. For example, cable has also impedance value. It's very hard to measure. It's very complicated.
Yeah, so Nezi Hoca, actually, Dr. Nezi Topaloğlu is more has more into this compared to me. So he's an electrical engineering background. So what would he have to say?
We were using vector network analyzer for the measurements. I think it was the easiest way. We even used a handheld vector network analyzer. Thank you, by the way, for the presentation. I think the questions asked by Aydın Bey were mainly, I think they are modifications that we can make, like changing the material or using a ring instead of a disc or an infinite plate. They are doable, but the issue is maybe the pre-stressing that Aydın Bey was mentioning, the pre-stress, and that may be a bit more difficult, but I think it's also doable. Yeah, these are my comments right now.
Okay.
I have a question regarding these sensors that you develop. Ufuk. These are going to be changed after the deposition of the chemical, right? Because once you change the natural frequency, it will not sense the same material anymore the same way, right? You deposit those and change the natural frequency of the plate, right? Then you have to switch it out.
Like a disposable. It's like
Disposable.
a disposable.
Yeah. Okay.
So it's like a lab on a chip concept, I think, possibly.
Okay.
It's like a cartouche. It's like a
cartridge.
Yeah, that you can change.
Excellent. Thank you.
You're welcome, sir.
Okay, thanks a lot for joining us then. Let's end this session. Thank you for being here and joining us. And it was a pleasure to have some of you from so many miles away. I think it's like 8 in the morning now in Texas, right? 8:15.
Yes, it is 8. Yeah, 8:15 in Texas. Yes.
Okay. So good
We're
morning.
waiting to see Mete here.
Yeah.
Soon.
Mete is just smiling. He's not responding to our inquiries about the papers. He's just smiling.
He will do it. I know him.
Yeah, he will do. He will do it. Actually, by the way, no, actually, we are waiting for him to do it. So we are waiting for him to give us the kind of draft manuscripts, right? And then, like 2 of them, we talked about the 2 manuscripts that you were preparing, right? You have 2 manuscripts. So probably we'll be in touch, hopefully, in the near future to talk about these manuscripts. So
yes.
if you pass by Turkey, please let us know.
Will do.
So that we can actually chat at least. Okay, so have a great afternoon, morning, wherever you are. See you.
Thank you very much. See you.
Bye-bye. Görüşürüz.